I'm here to present an article entitled Systematic Extraction of Tests from Object-Oriented Programs, which we in collaboration with my supervisor, Dr. Hassan Haghighi. Maybe the importance of object-oriented programs are so obvious because of uses and popularity of methodology among developers. For instance, I can mention GitHub. Open GitHub is a GitHub language and analyzing tool. As you know, the GitHub containing about 28 million open source projects. You can use GitHub to see different statistics like popular and most usage languages. Nowadays and recent years, the top popular language are JavaScript, Java, Python, and C++, which all support object-oriented program as mainstream. The object-oriented languages have amazing features like abstraction, encapsulation, aggregation, composition, inheritance, and etc., which can make a powerful solution for the most problem. However, these powerful features can make finding bugs and faults may be difficult because of some features like abstraction or encapsulation hides the state of objects from each other, and some other feature increase the complexity of relationship between classes and other program elements. Therefore, due to considerable effort and cost in the test phase, the automated or semi-automated testing approaches are helpful. Those automated techniques for object-oriented testing fall into two categories, the specification-based or program-based. In a specification-based approaches, test cases are extracted based on formal or semi-formal specifications. For example, in object-oriented context, the specification languages are like the Object-Z language or OT, and methods are systematic and extract effective tests along with sufficient article in terms of some expected outcomes that can reveal faults on class under test or program under test. This approach also extract tests containing valid method sequences based on the therefore extract readable, maintainable, and traceable tests. However, in the practice, we can mention some shortages. Like there are these approach usually they are not supported by major tools, and the formal specification on use the usual of critical system. And therefore, when there is no specification, this approach cannot be used. The difficulty of learning a new formal specification language or learning curve for developers can be mentioned also. On the other side, there are the code or program-based approaches which generate tests based on the program source code. We can categorize these approaches into two groups. The random-based approaches, they usually generate random method sequences for a class and evaluate each sequences to exhibit illegal behavior, for example, to exhibit a program crash. The other group of approaches can be categorized to a group such as structure-oriented techniques, which try to find a set of test inputs to reach high structural code coverage. In addition to code coverage criteria, this approach may use other criteria like the mutation killing rates. The structure-oriented techniques contain search-based techniques. A famous example is EvoSuite, which is a major tools in this area, and approach based on symbolic execution, which all try to find set of inputs to obtain high structural code coverage. The shortage of base approaches the shortages of code-based approaches are usually due to lack of functional and program logic specification. We can mention some shortages as in both approaches, some method sequences are not based on the class logic or program logic. Therefore, some of tests have invalid method sequences. Moreover, some test sequences are so complex, which leads to low readability, maintainability, or traceability of the test. Random-based approaches barely generate tests that can reveal logical error in the program. In other words, they often reveal error that lead to runtime exception like program crash or violation a set of predefined contracts like the self object is equal to self object and very general predefined contracts. The focus of a structure-oriented approach is on generating test data to obtain high level of code coverage, as mentioned. With respect to object-oriented paradigms, such tests are called intra-method tests. Intra-method testing is less important in object-oriented paradigm than for structure or traditional programs, because in object-oriented programs, the line of methods code and the complexity of the codes for a method are reduced, and software functionalities are indicated or modeled by a set of interaction of methods or interaction of classes, and so on. Tests in a structure-oriented approach are rarely equipped with effective oracles, which indicate the expected result part of test case.
Excuse me, Mohammed, can I slightly interrupt? So we have also a question from the audience. We still see the slide of object-oriented programming testing importance slide. Maybe should we see another slide, or that's fine? I just wanted to check with you. If you're changing the slides, we still see the same one.
Okay. You see my slide?
We see again the testing importance slides, large uses and popularity of OP and OP features.
Yeah, I changed the slide. Can you see it?
We unfortunately see still the same slides.
Which slide you are seeing?
OOP testing importance. I think it's second or third slide.
No change.
Unfortunately, still no change.
I think if you share again, it will be corrected.
Okay, I restart or resharing.
Okay, thank you. Okay. Now I see your slides. You're changing the slides again. The testing importance slide I see now. Now it changed. Called program-based testing approaches. If that helps, I can read the title. Okay.
Okay.
Okay. Okay. So I'll again leave the microphone to you.
Okay. As the code program-based testing shortages, I mentioned some of them. Random approaches generate many tests and redundant tests. Also mentioned that these tests not readable, maintainable, or traceable. And the structure-oriented approach mainly focus on generating intra-method tests. In the object-oriented paradigm, as mentioned, the intra-method testing less important than the traditional program because of the line of code and the complexity of method is reduced. So the functionality of software modeled by interaction of methods or interaction of some classes. The Oracle problem still exists in structure-oriented approaches, and these tests does not equipped with effective oracles, and maybe the tester should be present or indicate the correctness or incorrectness of tests. Our approach define a hybrid approach. Most of existing shortages are due to lack of class or program specification, as mentioned. One resource that can compensate for the lack of the class specification is statements in form of annotation libraries, assert statement using the code for purpose such as validating class field and methods. Nowadays, the programmers, mainly the Java programmers, use these mechanism to validate their object or classes. Our approach tries to use this validation statement in order to guide the test process. Our approach focuses on class testing instead of method testing. As mentioned, structure-oriented approaches focus on intra-method testing, but our approach tries to focus on testing the class itself. Also, our approach use these validation statements to provide oracles in terms of some assertion to reveal failure. The figure shows the proposed approach in the form of an activity diagram. The approach starts with a class in Java called the class under test as an input. The first component called model extractor component handle the extraction of class state variable as well as precondition or postcondition of methods. The state variable, or I mean class fields, and related constraints and condition are extracted from the class under test. And also the precondition and postcondition of each method can be extracted by this component. The next component is test machine component. Now, based on this logical model, the extracted logical model in previous step, and the class under test, it is the turn of this component to extract a test machine for that class. The test machine is a kind of a state chart whose state contains the state space of class and the transition correspond to class method calls. As an example, you see a very simple test machine for a class. It has two states with condition about size of a list, and transition are class method like add to list or remove from the list. The last component is test case generator component, which extract test case by mapping the paths of the extracted test machine to test cases. We also use logical condition in each state of test machine to form some test assertions. Model nowadays, many Java programmers, as mentioned, use different mechanisms to validate the state of object, like domain object, entity object, boundary object, or service methods. This mechanism helps developer to validate the state and behavior of class as normal Java logical expressions. This validation information and condition can be gathered from several sources in the Java programming language. The model extractor component tries to extract this information. For example, JSR 380 is a specification of the Java API for object validation, which uses some sort of annotation to validate objects. It's very common and used, and framework like a Spring support these annotations. For another example, there are validation and design by contract annotation library like Google Contract for Java or OVAL. This library use annotation and Java logical expression to validate objects. For another example, precondition library like Guava precondition, which is widely used among developer, or Apache Commons. These are in the form of methods to check and validate the parameters, the object state, and other cases. Last example is the built-in Java assert statement, which can define precondition and post-condition assertion for methods. An example is shown in the slide. The assert at the last of the method ensure the post-condition for this method. This article used the OVAL annotation library, but the model component can be expanded to use other type of libraries. Also, in addition, assert statement, which is the built-in feature in Java. For example, you see a simple stack class definition using OVAL framework. As highlighted in line 3, a condition is created on the class variable size using the assert annotation, which indicate that value of this variable must always greater than or equivalent to 0. This library can also use P to indicate condition for entering or leaving a method. For example, in line 6, a condition is indicated with post annotation, which ensure that after calling the method push, the top method cannot return a null value. A test machine is a test artifact, is an abstract test artifact containing abstract information that can be used to extract test cases. Each test machine can be defined corresponding to one method, multiple methods, or one class, or some classes. When we define the test machine for just one method, we can extract tests that covers intra-method tests. A test machine for multiple methods can address testing of interaction between these methods and cover inter-method tests. A class test machine address class testing and cover intra-class tests. And at the end, we also can define a test machine for some related classes. For example, a parent and the child classes, which these test machine can cover inter-class tests. However, the goal of this article and the test machine component is to extract the class test machine, which defined for a class, to use extract tests that cover intra-class tests. Inter-class test machine will be presented in future works. The test machine concept, talk about test machine concept. The test machine is kind of a state chart that consists of several states and several transitions. Each state contains a set of class variables with condition on them. A state, in fact, a set of state of a class. Test machine states make it possible to display the entire state of class in several abstract states. For example, as shown, if x is an integer class variable, a state of test machine can be represented like x greater than 10, which represent all state of the class where the value of the variable x is greater than 10. Transition connect states together. A transition in a test machine means calling one of the class method. So by calling a method, we transfer from one state to another. In a test machine, transitions are divided into two categories. The first type is valid transition. We have this kind of transition when by calling a method in one state, we go to a destination state, which is consistent with the logical model. For example, the post condition of the called method is hold. Another type of transition is invalid transition. In this case, the post condition of the called method does not hold in the destination state, or in the other words, the transition is not consistent with the logical model. As mentioned, a method test machine is defined corresponding to a method of a class. In a method test machine, states are defined on class variable or class field that are used in the body of the method. These variables are called effective variables. In addition, in a method test machine, all transitions represent a call to the method for which the method test machine is being defined. The following step describe how to extract the test machine for a method in a class. The first step is state variable partitioning. First of all, the input space of the effective variable are partitioned. To do this, first the type of each variable and the allowed values are queried from the logical model. Now, based on the type of the variable and its allowable values, partitions are created based on input space partitioning strategy. For example, for a numerical variable x, with allowable value of 0 or greater than 0, we can use boundary value strategy to create three partitions: x equals 0, x equals 1, and x greater than 1. The next step is constructing a pool of random object. In this step, a pool of random object with the type of the class under test. In fact, okay, excuse me. In this step, a pool of random object with the type of the class under test is built. In fact, the object pool is a finite set of objects with different value. This set can be created by different techniques that generate random objects from a class. In the proposed approach, a method inspired by random approach is used to construct random object of the class under test. In this method, after initializing an object by its constructor, random method calls are performed on the object. After each method call, a copy of the object as a sample is added to object pool. And the final step is connecting partition with transition. First, we consider all extracted partition as test machine states. Now, for each state, which we call input state, the sample objects that are placed in this state are selected from object pool. We call our method on this sample object. If after calling the method for all sample, the condition of one of the partition state is hold, we connect the input space to this partition. For example, for stack example, the effective variable for method push is size. We partition to 3 states. Now, by creating object pool, we can connect the push transition between this state. By merging two method test machine, a test machine can be obtained that produce different sequence of two methods call. We can derive test case from such a test machine to test different interaction between methods. Assuming that we have extracted two test machine A and B corresponding to methods A and B, this step should be performed to combine these two test machines. First, a copy of first test machine here, the test machine A, is considered as the resulting merged test machine. Now for each test, for each state, calling candidate state of the second machine, machine B, we perform the following step. If the candidate state is the same as one of the state of result, we ignore this state and copy it, transition to equivalent state in the result. If the candidate state does not have any overlap with result state, we add the candidate state with its related transition to result. If the candidate state has overlap with some result state, at most 3 new states are formed based on the notion of disjunctive normal form and replace the candidate state and the overlapped state in the result. For example, for our stack class, we saw how to extract push test machine in similar way, and now and pop a test machine. By merging them, we can obtain the merge test machine. At the end, after combining two method test machine, the resulting test machine can be merged with the third method test machine in a similar way. By applying this incremental and iterative process to other methods, we get the whole class test machine. Now we should indicate the initial state of the class test machine. For this all state condition that hold when a sample object created from different constructor, we add an initial transition to this state labeled with the related constructor name. Now each path in the test machine started with any constructor initial transition is a test case. If our test case has an invalid transition, we call this case as an error revealing test case, which should be failed when executed. If our test case does not have any invalid transition, we call this test case as regression test, which should be passed when executed and can be used for regression testing. Since a test machine is a graph, we can use different test adequacy criteria to derive different tests from the test machine. In this paper, we use prime path criteria to extract prime paths from the test machine. For example, such a test case can be extracted like this.
Excuse me, sorry, but I want to interrupt before the due to some timing issues at the beginning. Your time is actually up, but could you please wrap up the talk in a few minutes for the sake of
excuse me,
completing the session in time?
Okay.
Yes, but we of course we want you to complete the talk. Just I wanted to remind you to do that. Okay.
Also, our approach can be extended some opportunity based on the test machine abstraction. When we apply it in the a whole inheritance hierarchy, some opportunity can be seen. For example, reusing route inheritance, reusing test machine, or extracting tests for inheritance issue, or interclass tests that can be addressed in future work. We also apply our approach on a case study to demonstrate our applicability. The case study is a simple puzzle game called Tetris. It contains 14 classes. The class hierarchy as shown in the picture. Using our approach, test machine was extracted for each class. For example, a test machine for class plugin is presented here to evaluate the effectiveness of our test in revealing error. We first create 25 faulty version of tests using PET tool. Each faulty version has given 2 input to our proposed approach and the random tool. The random tool only detect 2 of this faulty version, but our approach is detect 80 faulty version. We also extend random predefined contracts by our oval annotation and prepare these custom contracts for random. In this situation, random generate revealing test case for 10 faulty version. We also we also generate a test that reveal a real bug in the implementation, and as a conclusion, as you see, we present a new approach to generate tests from object-oriented programs. Our approach leads a random test case generation process by extracting some facts and conditions about the program under test. We're currently expanding our approach to support our popular validation library and built-in asserted statements in Java. By this, our approach can be applicable for more Java programmers, and thus we can evaluate it on more case study, including industry or widely used open source software. We are currently extending our approach to drive tests for inheritance, polymorphism, and a specific feature of object-oriented language.